Fine. Good evening, everyone. So, in today's session, we will solve some of the problems from uh, mostly from digital electronics and uh, networks. And actually, today maybe I expected maybe the strength will be low. That's why we will only solve some of the problems. We don't cover much topics. So, let us see this. This question was given in GATE 2015. EE set 1 for 1 mark. So the question is the voltages developed across 3 ohm and 2 ohm resistors shown in the figure are 6 volts and 2 volts respectively with the polarity as marked. What is the power delivered by the 5 volt voltage source? So this is the network given. So we need to find out what is the power delivered by this 5 volt source. What's the power delivered by this 5 volt source? We need to find out. So please confirm me. You can hear me, right? Since I joined with mobile net, I'm not sure whether the screen is visible. And okay, fine. Okay, thank you. Now we need to find out what is the power delivered by this source. So we can apply here, let us say, some kind of KCL. So let us say we have some network. Let us say we have some complex network. Maybe there are many resistors, capacitors, and inductors like that. And let us say we have connected some source here. Some source, let us say voltage source. Some voltage source, and this is, let us say, internal resistance of voltage source. Now let us say some current the network is drawing some current from the voltage source is. Now is is entering into the network. Okay, so whatever current is entering into the network, same current will come out of the network, right? Isn't it? Let us say this is is1 entering, is2 leaving. So is1 equal to is2, right? Isn't it? I think you have seen this, right? Similar to like KCL, let us say we have some node. So this I think you have seen, right? KCL. Let us say we have some currents here. I3 is leaving, I2 is entering, I4 is leaving, and I5 also leaving. So we know entering currents equal to leaving currents. Entering currents I1 plus I2 equal to leaving currents I3 plus I4 plus I5. This you know, right? Similarly, for a network, if it is connected to some source, so whatever current is entering into the network is same as current leaving from the network. So that thing we will use here. Now, if you see here, let us say network N2 you consider. In network N2, whatever current entering into the network, that will be equal to the whatever current leaving from the network. From this network, whatever current entering into the network will be equal to the whatever current leaving from the network. Now you see that 6 volts one, the upper branch you see 3 ohm resistor and 6 volt, there is a voltage drop. Now what is the current here? What is the current here? Let us say, now we know, right, this one. Let us say we have some resistor. Okay, when there is a current is going like this, so resistor always dissipates energy. So what is the voltage? What is the polarities of voltage? This is the voltage across the resistor. So VR equal to I into R, right? So in a resistor, always when a current is going, so the voltage across a resistor, the polarities will be wherever the current is entering, there it is plus, wherever current is leaving, there it is minus, right? Let us say capacitor, the resistor always dissipates energy. Resistors always dissipates energy. If you take capacitors or inductors, based on the situation, they may dissipate energy, or what to say, they may absorb energy or deliver energy, right? So let us say capacitor you take. Now let us say in a capacitor, voltage across capacitor is VC. Let us say current is entering at the plus terminal in the capacitor. The current is entering at the plus terminal, then current is sorry, the capacitor is, it is like absorbing energy. Okay, energy or power, whatever it may be. And in a capacitor, let us say this is a capacitor and voltage across capacitor is this one. Let us say current is leaving from the plus terminal, then in that case it is acting like a source. Let us say it is acting like a source, so that means it is delivering energy. Similarly for inductor, similarly for inductor, okay, when the current is entering at the plus terminal, then it is absorbing energy. When the current is leaving at the and leaving at the plus terminal, then it is delivering energy. Okay, I think we have seen that. Let us say we have some network like this, plus minus, and maybe the capacitors, something like this. We have some network. Now let us say current is entering here. Now current is leaving from plus terminal in this voltage source. That means this voltage source delivering energy. These things, and let us say in some network a voltage source is there, some like V2. In that voltage source, the current direction is like it is entering at plus terminal. Then it is not delivering energy. It is not delivering energy. It's absorbing energy. Okay. But resistor, all, let us say you have seen, I think, DC transients, right? You might have seen DC transients. You have some voltage source here, that is the step voltage here. At t equal to 0, voltage become V. Before t equal to 0, voltage is 0. Uh, then, yeah, the power came. Just give me 1 minute. Yeah. So, this is here. You have voltage here, and maybe some resistor, and maybe some capacitor. Now, when the voltage is present, now capacitor gradually charges, right? Capacitor voltage gradually charges. In that case, this is the capacitor voltage. Now, current enters here. So, here the capacitor absorbs energy. Okay. Now, let us say there is no voltage source. Voltage source is not there. Only capacitor charged, let us say. Capacitor is fully charged. Then we removed the voltage source. Then what happens when we remove the voltage source? Then what happens? Let us say capacitor fully charged to VC, some V volts. Okay. Now the capacitor voltage is V. Now the capacitor delivers energy actually. Now the current through the capacitor is like this. Now the capacitor delivers energy. But in the both the cases, in resistor here current is entering here. In the both the cases, resistor, always in resistor, uh, wherever the current entering, that is the plus terminal, and wherever the current leaving, that is the minus terminal. Okay, will flow from plus to minus. Let us say current is going through a resistor like this. Okay, the voltage developed across this is the, let us say, VR. Then plus is where the current is entering, minus is where the current is leaving. That is always true for resistor, but in a capacitor and inductor, depending on whether it is absorbing energy or delivering energy, the polarities will change. When it is absorbing energy, then the current will enter at the plus terminal. Let us say capacitor voltage, this one, current will enter plus terminal. When it is delivering energy, let us say the capacitor voltage is VC, then it leaves from the plus terminal. Okay, now in this case, let us come to this case. Now can you tell me, in this 3 ohm resistor, can you tell me in this 3 ohm resistor, whether, what is the direction of current? Can somebody please tell me what is the direction of current in this 3 ohm resistor? Can somebody tell me what is the direction of current, the top branch? N2 to N1, because resistor always current enter at the plus terminal. So this is the current direction. Let us say this is I1. Now what is I1 here? I1 is, we know, V by R. So V by R. So voltage across resistor is 6 volts and resistance is 3, so 2 amps. Now what about the second branch? Since the plus is here, so current enters here. So I2. So I2 is entering the network 2. Now what is I2 here? I2 equal to 2 by 2, 2 volts by 2, so 1 ampere. Okay, now what is the current? Let us say current here, since they asked in the question what is the power delivered by 5 volt source, we can see it in the question. They asked power delivered by 5 volt source. Since it is delivering, means in the source, what will be the direction of the current? 5 volt source. Can somebody please help me? Since the source is delivering power, so the current leaves the source, yes, negative to positive, that is leaving from plus, that is I3. Now in this case we have seen, for a network, what is the current, total current entering should be equal to the total current leaving from the network. So let us say you take for network 2, whatever the current entering should be equal to whatever the current leaving. So current entering is what? Entering equal to current leaving. So current entering is I2 plus I3. So current leaving is I1. So from here I3 is what? I1 minus I2. I1 is 2 and I2 is 1, so 1 ampere. Now we know power. What is the power delivered? Now power equal to power delivered by 5 volts source is, we know, voltage into current. So voltage is 5 volts and current is 1 ampere. So power delivered equal to 5 watt. Is that okay? Similar to how we apply KCL for a node, we can apply for a network also. Entering current to a network equal to leaving currents. And here we should know the polarities, current from where to where the current is going. Since already they have given in the question, maybe sometimes they may give question. Now what is the power across 5 volt resistance, maybe something like that they must. And the options, they may give 5 volts delivered, 5 volts absorbed, 10 volts delivered, 10 volts absorbed, something they may give. That kind of question also may get. So based on the polarities, whether it is leaving from plus terminal or entering into plus terminal, power absorbed or delivered, we should. So 5 watts here delivered. Okay. Fine. Now we'll see another question. Yeah. This is the question given in GATE 2015 ECE set 1 for 2 marks. The question is, all logic gates shown in the figure have a propagation delay of 20 nanoseconds. Okay. And let A equal to C equal to 0 and B equal to 1 until time equal to 0. And for t less than 0, they are these values. And for at t equal to 0, all the inputs flip. Okay. And they remain in that state for t greater than 0. Output z equal to 1 for a duration of dash. Okay, this is the question given. This is from digital electronics. Now generally we study like we assume like gates are ideal gates, and we will generally solve the problems, but here they have given the gates having some propagation delay. You know, right, the propagation delay, suppose we have some gate, let us say not gate, it is having some propagation delay. Let us say we are giving some input at t equal to 0, it is changing from 0 to 1. The output should be ideally this one, right? Because it's inverter. But if it is having some propagation delay, let us say 20 nanoseconds, let us say, given in the example, then instead of this, it will change not immediately, it will change after 20 nanoseconds. Okay, that is the propagation delay. Now, after the application of input, the output will not change immediately. It will take some time. That is nothing but the propagation delay of the gate. Now, for each of the gates, the propagation delay here it is given. TPD is 20 nanoseconds. Now, let us draw these waveforms. Now, A and C are 1 and B equal to 0. Now, I am drawing these waveforms. Now, sorry, A and C are 0. This is t equal to 0. This line is t equal to 0, let us say. This is for t less than 0 and t greater than 0. Now this is A, this is B and C. In the question it is given A and B, C are 0 for t less than 0 and B is 1. For t greater than 1, A is 1, B is 0 and C is 1. Okay. Now signal is applied. Now this is the circuit. Okay. Now we need to find out for what duration of the time output is high. Now first we will calculate B bar. First we will find out B bar, since this is right, this is B bar, because B is going to inverter. First we need to find out B bar. So I'm just drawing here B bar. So what will be B bar? Ideally B bar should be something like this, right? Ideally B bar should be something like this, because it's inverse operation of B. It is something like this, but there is a propagation delay of 20 nanoseconds, right? So there is a propagation delay of 20 nanoseconds. So instead of changing here, now B we are applying here, B bar will get, but after 20 nanoseconds propagation delay, at t equal to 0, B is changing from 1 to 0. You see here B is changing from 1 to 0, t equal to 0. Ideally B bar should change from 0 to, sorry, B bar is not this one. it should change from 0 to 1, right? B bar should change from 0 to 1, because when b is 1, B bar is 0, and when B bar is 0, so when B is 0, B bar is 1. So this is B bar. Ideally it should be like this, right? When B is 1, B bar is 0, and when B is 0, B bar is 1. Now, but there is a propagation delay of 20 nanoseconds, right? Immediately it will not change. Now it will change after a delay of 20 nanoseconds. Now this is our B bar actually. So the time delay here is 20 nanoseconds. Okay, let's say this we will say T1, that is 20 nanoseconds. Okay, you got it right? That is B bar. Now we have B bar. Let us say output of this AND gate is some P. Output of this AND gate is P. That is what? A plus B bar. Sorry, AB bar. Sorry, output of P is AB bar. That means, so I'm drawing P also here. So P is what? Equal to AB bar. A we have and B bar we have. So output of AND gate is high only when both the inputs are high. Otherwise it is low, right? Now ideally, assume there is no propagation delay. What should be P bar? I'm drawing here. Please tell me whether it is right or wrong. Now P depends on these two. Sorry. P depends on A and B bar, right? P depends on these two. So when both are 1, then only P is 1. So up to t equal to 0, both A and B bar are 0, so P also 0. So I'm drawing this ideally. Now from this interval, from T to T1, let us say this is T0. So T0 to T1, A is 1, but B is 0, right? So here also AB bar, this one. Now from T1 onwards, from T1 onwards, both B bar and A both are high, right? So output is 1. This is ideally. So what I am doing, see, for T naught, that is for T less than 0, that means this interval. For T less than 0 seconds, both A and B bar are zeros, you can see here. So that P, that is A and B bar is 0, end operation, right? Then between this the next interval, that is 0 to 20 nanoseconds, A is 1 but B is 0, that's why output is 0. But after that, for t greater than 20 nanoseconds, this interval you consider the last interval. Now here both B bar and A are 1, so the output is 1. This is ideally when the AND gate is not having any delay. But there is a 20 nanosecond propagation delay, right? So instead of this, what waveform we'll get? The P will be not this one. P will be, there is a delay of 20 nanoseconds. Instead of this, we will get, this is P, the red one. Okay, you got it right? This one. Okay, so here there is 20 nanoseconds delay. Let us say this is T2. What is T2 now? T0 is 0. Here T0 is 0. T1 is 20 nanoseconds. T2 is 40 nanoseconds. So that is P. You got it right? Now what is the next one? You see the XOR gate. XOR gate, what are the inputs for XOR gate? C and P are the inputs for XOR gate and Z is the output. So C and P are the inputs for the XOR gate. Here we have C here and P here. I'm just drawing again C and P. So here we have C here. This is C and this is P. Now output is, final output is Z. Z is what? P XOR C. So you know, right, XOR operation, you know, right? XOR operation. So when any one of the inputs are, when both the inputs are 0 or both the inputs are 1, then output is what? 0. For XOR gate, you know, right? So let us say P and C Z. This is XOR gate, right? And if any one of the inputs are 1, then output is 1. This you know, the truth table of XOR gate. When both the inputs of XOR gate are either zeros or ones, output is 0. And any one of the inputs are 1, then the output is 1. Now I am drawing Z here. You can see by considering C and P, I am drawing Z here. Now let us assume there is no delay. First I am drawing Z here. Now up to T naught, both C and P both are zeros. So Z is 0. Okay. Now from T naught to T1, from T naught to T1, now C is 1 and P is 0. So one of the inputs is 1, so output will be 1. Okay. And from T1 to T2, C is 1 again and P is 0, so output is 1. And after T2, if you check after T2, both C and T2, C and P both are high, so output is low. This is the signal, output signal Z, assuming that there is no propagation delay for the XOR gate. So now what is the duration here? How much time it is high? 40 nanoseconds, right? T2 up to T2, so 40 nanoseconds from T0 to T2. But there is a delay, right? So actual Z is something like this. Since there is a delay, actual Z is something like this. So there is a delay of 20 nanoseconds. So actual Z will be somewhere, will be high here and up to here. Yellow one is the actual Z1. So for how much time it is high? 40 nanoseconds. So that's what it is asked in the question. So for t greater than 0, output Z equal to 1 for a duration of dash. So 40 nanoseconds is the answer. Is that clear? So we can solve this just by drawing these waveforms. Others also, I think Bunty he answered yes. Others? Yeah, fine. So mostly when in the, especially in digital electronics, when they are asking about this kind of delays and all, when you want to solve a circuit or in it, let's say a digital circuit using delays and all, better to draw the waveforms, then it will be clear. Otherwise, we'll get confused. Okay. Since here each and every gate is having 20 nanoseconds delay, so first you draw the inputs and output of each gate you draw. So first gate output is B bar I have drawn, second gate output is, let us say I'm saying P, that is A and B bar, third gate output is P XOR C. Each and every one I'm drawing. First I'm saying, let us say that's ideal one, but there is a delay, then I'm shifting that one. So like that, if you do one by one, you will not have any confusion. Okay. If it is clear, then we can move on to the next part. Can we move to the next problem? Yeah, thank you. So this is the next question. This question was given in GATE 2015 ECE set 1 for 2 marks. The question is the Boolean expression f of x, y, z is given. Okay, Boolean expression f of x, y, z given. Convert into the canonical product of sum form. Okay. So something is given, we need to convert into canonical POS form. So canonical POS form is also called as product of max terms form. Hope you know this. So Boolean functions we can represent in two ways. Let us say we can represent in standard form. Like one type is SOP form and POS form, sum of products form and a product of sums form. This I think you know. Let's say you have some function f of a, b, c. Then SOP sum of products form something like this: a, b plus b bar c, something like this. And product of sums form is something like this: a plus b bar into b bar plus c bar, something like this. And another type of representation is canonical forms. So in this we have canonical SOP form. Canonical SOP form are also called as sum of minterms form. Sum of minterms form and canonical POS form. This is also called as product of max terms form. What are minterms? What are max terms? We have explained in our previous class. So we will see here. Now, if you see here, what is f here? F of x, y, z. In terms of minterms, what are the minterms here? So we know in minterm representation, a variable is represented with 1, variable complement is represented with 0. So x bar here 0, right? I'm writing x bar 0, y is 1, z bar is 0. And the second so what is that minterm? So minterm, that is what? 2, right? Plus whatever the second one, x is 1, y bar means 0, z bar is 0, that is minterm 4. Next is x is 1, y is 1, z bar is 0, so minterm 6, minterm 6. And x, y, z all ones, x1, y1, z1, so this is minterm 7. So what we have is sigma m of, we can represent like this, right? 2, 4, 6, 7. This is sum of minterms form. This is what? F. So this is F. Now I want F bar, let us say F bar. What is F bar? You might have seen, right, from minterms, sum of minterms form and all, we can write the truth table, right? What is F bar other than these minterms, right? F is sum of 2, 4, 6, 7 minterms. F bar is other than these minterms. Since it is a f is a 3 variable function, how many minterms it will have? 2 power 3. 3 variables, 2 power 3, 8 minterms it will have. So it will have 8 minterms. So what are the minterms? M0, M1 up to M7, right? Now in this case, what is F bar here? Other than what are the minterms present in F. So sigma m of 0 is not there in that, 1 is not there, 2 is there, then 3 is not there, 4 is there, 5 is not there. So this is F bar. Got it right? We have F, from that you can get F bar. Now to get canonical POS form, what is this form actually? This form is canonical SOP form, right? Canonical SOP form, actually what we have, SOP form, or sum of minterms form. Sum of minterms form. Okay. Now to get the other form, what I take, I will take F bar whole bar. I will take F complement whole complement. From F I found out F bar. Now again if I take complement of that, I will get again F, right? So that means again I'll get F when I take a complement of this. Is that okay till here? So these kind of conversions, what we need to take from F, sum of minterms from, you find out F bar, then you take F bar whole bar you take. So this one you get sigma m of this. So F is what? F is F bar whole bar is what we got, sigma m 0 1 3 5 whole complement. So that means these are what, sigma m means m0 plus m1 plus m3 plus m5 whole complement, this one, right? So you know De Morgan's law. This how we can write, m0 complement and m1 complement and m3 complement and m5 complement. Okay. Now you know uh, minterm complement, last class we have seen, equal to max term, right? Sorry, max term, right? The complement of a minterm is equal to the max term. Let us say mi is a minterm, so its complement is max term and vice versa. So if m naught is a minterm, its complement will be max term naught. Sorry, max term. Okay. Now, so what we got? This is f. So f is m naught complement is what? Max term 0, and minterm 1 complement equal to max term 1, and minterm 3 complement is max term, and minterm 5 complement is max term 5. Now we know max term representation, variable is represented with 1, sorry, variable is represented with 0 and variable complement is represented with 1. So here m naught means x, y, z is the max term m naught, and m1 is x plus y plus z bar, and m3 is x plus y bar plus z bar, and m5 is x bar plus y bar, sorry, x bar plus y plus z bar. Okay. So from this, which option? X plus y plus z plus x plus y plus z bar. Option A is the correct one. So from this, option A is the correct one. Yeah. Now, is that okay? So how to solve this kind of problems is, so first it is given in the sum of minterm form. Then you take complement of it. That means the minterms other than whatever present in F, that is nothing but F complement. So you take again complement. It is same as F. So you apply De Morgan's law. Then you know complement of min term equal to max term. So in this way we need to convert. If you don't have any doubts from this, we can go to the next problem. Fine, we are going to the next problem. So this problem was given in GATE 2015 ECE set 1 for 2 marks. The question is a 3 input majority gate is defined by the logic function. Okay, a 3 input majority gate is defined by the logic function AB plus BC plus CA, M of A, B, C equal to. So this is M. Which one of the following gates is represented by the function? Okay, so M of something is given, this one. Okay, no, actually this we can solve by using like we can solve in SOP form, since it is given which form, SOP sum of products form it is given. This is SOP form, right? This we can solve in SOP form, but it is somewhat difficult. It will be lengthy to solve. So instead of that, we will convert into sum of minterms form. Then we will solve it. That will be easier to solve. So what the question given is this one, right? So in this, I'm saying this as X. So this one I'm calling as X, and this one I'm calling as Y, and C I am calling as Z. Now what we require is M of X, Y, Z actually. Okay. The first one I'm calling as X, second one I'm calling as Y, third one calling as Z. I want actually final one M of X, Y, Z. But what is M of X, Y, Z? Since M of A, B, C is given, right? AB plus BC plus CA. In the similar way, so this one will be XY plus YZ plus ZX. This is our M. Now one by one we need to find out what we require. Now first we will solve this in sum of minterms form. Now for that purpose what I am doing, I am converting. First I want to find out X. What is X? X, you know, from there M of A, B, C whole bar. This is X. Now to find out X, I want to find out M of A, B, C in SOP form, sum of minterms form, sorry. M of A, B, C is what? AB plus BC plus CA. You know how to convert SOP form into sum of minterms form. In the first one, in the first term, what to say, C is missing. So I'm just multiplying this with 1, let us say. So instead of 1, without changing the function value, C plus C bar I can write. Okay. In the second one, second term A is missing. So instead of that, I am writing like this. The third one actually B is missing. So this one I'm writing here actually CA. Here actually B is missing. So CA, and you can do AND operation with 1 without changing its value. So since B is missing, instead of 1 I am writing as B plus B bar. Since B plus B bar is 1, so it doesn't change its value, right? In this way we will convert into sum of minterms form. So it will be CA into B plus B bar. Now expand this, you will get ABC plus ABC bar plus ABC plus A bar BC plus ABC plus A B bar C. If you see here, A B C is repeated 3 times. That is actually min term 7, right? Min term 7. Now A B C bar. This one is what? This is min term 6, and A bar B C. This is min term 3, and A B bar C. This is min term 5. So what you get, M of A B C, actually M of A B C is min term 3 plus min term 5 plus min term 6 plus min term 7. So this is nothing but sigma M of 3, 5, 6, 7. This is M of A B C. So what is X? But X I want as X is what? From here, what is our X? X is M bar of A B C. So what is M bar then? Other than those terms. In M, 3, 5, 6, 7 are there. Just now we have seen how to find out the complement. So this will be sigma M of 0, 1, 2 and 4. Okay, 0, 1, 2, 4. This is X. Okay. In terms of ABC, actually X is a function of ABC here. Okay, in terms of ABC, X is a function of ABC. Now next we'll find out Y. What is our Y here? Next step is to find out Y. Our Y is what? We can see here our Y is M of A, B, C bar. So M of A, B, C bar. So expand this. What is this? Because M expansion is given AB plus BC plus CA. So this is nothing but AB plus BC bar plus AC bar. Similarly, you convert into sum of minterms form. Again, I'm writing AB into C plus C bar plus B C bar into A plus A bar plus A C bar into B plus B bar. Similar procedure I'm following. So ABC plus ABC bar plus ABC bar plus A bar B C bar plus A B C bar plus A B bar C bar. So again this is min term 7 and this is min term 6. This is also min term 6. This is min term 2. This is min term 6 and this is min term 4. So what you are getting here, min term 2 plus min term 4 plus min term 6 plus min term 7. Okay, this is your Y. So Y is what? Actually Y is a function of A, B, C. Okay, in terms of A, B, C, Y is a function of A, B, C. This is what? Sigma M of 2, 4, 6, 7. Similarly, X is also a function of A, B, C. Okay, X is also a function of A, B, C. Fine. Now the other one is, what is our Z? Z is nothing but only C. You can see here Z is nothing but only C here, right? Now Z is nothing but only C. So again we need to convert into which form? Sum of minterms form. So let us say I am doing AND operation with 1 and 1. It will not change. Since A and B are missing, so I'm multiplying with A plus A bar and B plus B bar. So I'm quickly writing here, you will get something like this: A B C plus A bar B C plus A bar B C plus A bar B bar C. What you get here is sigma M of 1, 3, 5, 7. Okay. So finally what I want is M of X, Y, Z, right? So what I want is M of X, Y, Z. This is what we want, right? Finally, that is nothing but what? XY plus YZ plus ZX. So XY plus YZ plus ZX. Now what is x? X we have seen sigma m of this one, right? 0, 1, 2, 4. So sigma m of 0, 1, 2, 4, and y is sigma m of 2, 4, 6, 7. 2, 4, 6, 7. Okay, plus yz is what? Y is sigma m of 2, 4, 6, 7, and z is sigma m of 1, 3, 5, 7. Okay, the next is zx. Z is sigma m of 1, 3, 5, 7, and x is sigma m of 0, 1, 2, 4. Okay, now we know, I think you might have know this. See here you have like two functions. This is a sum of minterm form. There is an AND operation here and another sum of minterm form here. You can see here clearly. Sum of minterm form sigma m 0, 1, 2, 4 and sigma m 2, 4, 6, 7. So when there is an AND operation, you know that AND operation, in both of them the minterms should be present, then only we will get. So what are the minterms common in both of them? 2 is common in both of them and 4 is common in both of them. Those minterms only will present and all minterms will vanish. Hope you know this. So from this, the first term what we get, this one I am writing. The first term, what are the minterms common? Sigma m of 2 and 4 are common. 2 comma 4. Okay. Now the second one you take, this one. What are the minterms common in this? Only 7 is common, right? Only minterm 7 is common here and here. That only will present. Since there is an AND operation, right, between them. So minterm 7 will come here from the second term. And for the third term, in this third one, what is common? Only minterm 1 is common. So only that one will be present here. So minterm 1. Okay. So sigma m of 2 comma 4 means it is m2 plus m4. The next one is m7. The next one is m1. So this is sigma m of 1, 2, 4, 7. This is what final one, what final output what we want. That is m of x, y, z. I am telling that m of x, y, z is the final output we want. Sigma m of 1, 2, 4, 7. Sorry, the final one. I'm saying, let us say this is f. Whatever we want, this we say f. Okay, this is f. You can say f of a, b, c. These are the binary variables, right? Independent variables. So this is very standard one. I think you know this. This is either XOR operation, A XOR B XOR C, or XNOR operation. Hope you know this. Both are same. These minterms 1 to sigma m of 1, 2, 4, 7. This is A XOR B XOR C or A XNOR B XNOR C. Hope you know this. When the number of inputs are odd, when the number of inputs are odd, then XOR equal to XNOR, right? I think you know this. That is, let us say A XOR B XOR C equal to A XNOR B XNOR C. Okay. And when the number of inputs are even, then XOR is complement of X naught. This you know this, right? That is, you have two inputs, then A XOR B, that is equal to A XOR B complement, or four inputs or six input like that. Since we have three inputs, right? XOR equal to XNOR, both are same. Okay. Now the options, what are the options given? First option is a 3-input NAND gate. This is wrong. Second option is a 3-input XOR gate. B is right. Third option is 3-input NOR gate. This is wrong. And fourth option is 3-input XNOR gate. This is right. Actually, for this question, two answers are correct. Either B or D, both are correct. Okay. Is it okay? Maybe you may wonder like how I have written directly here XOR gate. You can check this. This is very standard one. These minterms is nothing but minterm 1 plus minterm 2 plus minterm 4 plus minterm 7. That's very standard one. You can write and check later. It's 3-input XOR gate or 3-input XNOR gate. Is that okay? Uh, for others, do you have any doubts from this? Last point. Which one? This one? When the number of inputs are odd, this one, right? Yeah. Now, let us say the number of inputs are even. I'm taking. Let us say you have an XOR gate. Inputs are even. I'm taking. So, what is the output? A XOR B is AB bar plus A bar B. Right? Now, for an XNOR gate, let us say for an XNOR gate, two input XNOR gate. You know what is the expression for XNOR gate? AB plus A bar B bar. Okay. Now you take the complement of this one. A XNOR B complement you take this one. So A XNOR B complement you take, that is nothing but AB plus A bar B bar complement. Okay. Now you express this. So expand this. This become AB bar and A bar B bar whole bar. So this will become A bar plus B bar to A bar plus B bar whole bar. That is nothing but both are like A complement whole complement. I can write normal. So this one. Now expand this again. A bar A plus A bar B plus B bar A plus B bar B. These things will become 0, and what we are left with is A bar B plus A B bar. So this is nothing but A XOR B. Okay. When the number of inputs are even, like this, you can check later also. And the number of inputs are even to an XOR gate, then XOR gate complement is XNOR gate and XNOR gate complement is XOR gate. Okay. So vice versa. Let's say 4-input XOR gate I'm taking. 4-input XOR gate. Let us say A, B, C, D. Output is F. Okay. This is A XOR B XOR C XOR D. If I take complement of F, okay, then I'll get this one. The other case, what I'm telling is when the number of inputs are odd, then both XOR gate and XNOR gate both are same. Uh, that means when the number of inputs are odd, let's say three inputs I have A, B, C. This is XOR gate. So output is A XOR B, sorry B XOR C, and an XNOR gate also you take. This is an XNOR gate. A, B, C. Output is A XNOR B XNOR C. Now expand these two. Whatever expression you'll get and whatever expression you'll get, both will be same. Later you can expand this. So you can get sigma m of 1, 4, something like that you'll get it. 1, 2, 4, 7. You can expand this. 1, 2, 4, 7. Both you'll get the same thing. Is that okay? It will be valid for any number of inputs. Even 5 input XOR gate or 5 input XNOR gate, both will be equal. Bunty, is that okay? Doubt got clarified. Okay, okay, fine. Maybe it's time for other session. You can join that session. If anybody is having any doubts, they can stay back in this.